and welcome to ESC Live. We are here today from Kensa Heat Pumps factory in Truro, Cornwall, and you're going to be learning all about this exciting future technology and current technology that hopefully will be heating our homes and our buildings in future. I'm Dr. Natalie Whitehead. I'm a former engineer turned physicist, and now I'm working alongside my colleague Dr. Alice Mills to set up Exeter Science Centre. We want to set up a science centre of the whole of the southwest. We're doing this live stream today alongside Professor Adam Feldman from the University of Exeter, who's a renewable energy engineer. So what are you going to be learning about today? And by the way, of course, you're going to be meeting some amazing engineers who will introduce you very shortly, who are working here in Cornwall at Kensa Heat Pumps. Today you're going to be learning straight from the experts all about ground source heat pumps, what they are and how they make them here at the factory. You've got a worksheet as well to fill in, so please have a look to fill in the blanks and make sure that you're answering all of those. Partway through you'll have a midway challenge, so get ready to answer an engineering challenge and solve that with your teacher. And I'm going to pass over to Alice now to give a bit of an introduction to the site.
Brilliant. So let me just introduce you to some of the amazing engineers that are going to be talking you through what they do here today. So we have got Ollie Sanders over here. He's the senior test engineer. We've got Dr. Ben Thorpe. We've got Darren Veal. Ben Thorpe is a senior research and development engineer. We've got Darren Veal over here, who is an installer, development and training manager. And later we're going to be joined by Dr. Amy Featherstone, who is the innovation lead. And then finally, here we have got Paul Eveleigh, who is the managing director of Kensa. So Paul, we'll start with you. Thank you so much for letting us come and do this today. It's really exciting.
You're welcome.
So yeah, what do you do here in summary?
So Kensa is the UK's largest manufacturer of ground source heat pumps. Ground source in that they take the heat from the ground and compress it and put it into heating systems in homes and in commercial buildings. All of our heat pumps are manufactured here on site. Typical projects that they go into, well, the high end go into high-end homes, your installer developers, grand designs, that kind of home. But at the other end, we have installed literally thousands of our shoebox heat pumps into social housing, converting tower blocks from natural gas boilers, taking those out because we don't like burning things for heating anymore, and also replacing things like electric storage heaters, which are expensive to run and actually not very effective. So replacing all of those with small tube box heat pumps in every apartment or social housing house connected to a shared array of pipes in the ground, in a ground array.
That's so cool. Fantastic. So you're going to have a tour of the process here and how the pumps are made. We'll hand over to Adam for the tour.
Thank you very much, Alice. So I'm Professor Adam Feldman. I'm a Professor of Engineering with the University of Exeter, but based at the campus here in Cornwall at Penryn. And what we're going to learn about today is an amazing machine. It's called a ground source heat pump. In a few years' time in Britain, we've promised we won't heat our homes anymore using fossil fuels like gas or oil. And probably the most frequently used machine to heat our homes and our buildings is going to be the heat pump. And how will this work? Because you're going to see a lot of these machines around. It runs on an amazing piece of physics, a thermodynamic loop called a refrigerant cycle. It's called a refrigerant cycle because we use this mechanism in our fridges at home, in our kitchens, in our freezers. But we can run this machine the opposite way round to transfer heat into a building in order to take heat from outside, perhaps from the ground or from the air or from a body of water like a lake at low temperature, and take a small amount of heat energy from these colder, lower temperature environments and use our heat pump to concentrate that heat up to a higher temperature and lift it into our buildings. Now, the most important thing as we go round and look at the factory is to realise that heat and temperature are not the same thing. Heat is a variety of energy, whereas temperature is a property of that energy. What I'm saying is something that's at a very low temperature, perhaps minus 50 centigrade, can in fact have more heat energy in it than something at a higher temperature, like 200 centigrade, which might actually, paradoxically, strangely, have less heat in it. The way the heat pump works is to have about 5 important components sitting inside it. Probably the most important component is a liquid, a fluid, called a refrigerant. And again, it's called a refrigerant because we've been using them in refrigerators for many years. But here it's being used to raise the temperature. And what a refrigerant is a fluid that changes its phase from liquid to gas. In other words, it boils at a fairly low temperature. Now, the machine that in a minute Paul and the team are going to show us works by having such a refrigerant inside it. There are 4 components that refrigerant goes through. 2 of them are heat exchangers. One is called the evaporator and the other is called the condenser. And between the evaporator and the condenser is a compressor, which is a bit like my bicycle pump, to raise the pressure of the refrigerant. And then going back to take the fluid, the refrigerant, back from the condenser to the evaporator, something called an expansion valve. We take heat at low temperature from the ground to the evaporator, where we boil the refrigerant. The boiled refrigerant goes into the compressor, and by compressing it up, and I'm sure as physics students you all know the equations, pressure times volume divided by temperature is a constant, PV over T is a constant. By raising the pressure, we raise the temperature of our boiled refrigerant. We then run that hot, higher temperature refrigerant through the condenser, which takes the heat out into the building, either to radiators or to underfloor heating, or sometimes to machines that blow warm air into the building. We then take that refrigerant, which has had the energy, the heat energy taken out of it, back through an expansion valve to drop its pressure, and it's all ready to be boiled again as we go back into the evaporator. So, Paul, can we go on a tour of the factory and see this machine being assembled?
We absolutely can. Let's go and see how that physics is turned into mechanics. So we walk through. So this is our factory. It's 4 production lines combined to produce heat pumps. We produce a variety of heat pumps. That's a 6 kilowatt shoebox just in front of you. We do a smaller version of that, and we do a larger range called EVOs, depending on the type of building. They all run through this line. The factory currently at peak produces 1 heat pump every 15 minutes. It starts at the far end of the factory. I'll walk our way through it. So at the beginning of the heat pump manufacture, we start with a kit of components. This kit of components we've just discussed. So some insulation, but more importantly, 2 heat exchangers. One side connected to the ground array, to the water in the ground, one side connected to the heating system, and in the middle, the refrigerant circuit that we've just discussed. This collection of pipes is brazed together by our guys in the hotworks cell to create the refrigerant circuit, which I can show you in a second.
So in the evaporator, we boil this refrigerant, just like this little model here.
Okay. So this is the first cell of assembly, okay? So these guys are taking that kit, which has been put together into a refrigerant circuit on those shelves there. They're taking a chassis with a compressor on it, and they build it all together to give you a refrigerant, to give you a full heat pump refrigerant circuit, okay? So we can see the 2 heat exchangers insulated. This particular heat pump has a twin compressor that run in parallel, okay? A water pump, that's pumping the water into the ground, okay? So we pump it down and it returns, okay? And most importantly, the component you mentioned earlier, okay? An expansion valve here, okay? Without the expansion valve, the compressor will just pump the refrigerant in a circle, it'll do nothing. the expansion valve controls the flow of that gas and limits it so that you get compression to give the temperature increase that you talked about.
And what's this coiled bit here for?
The capillary basically is part of the process of managing the level of compression. Okay.
Sure.
That there. So at this stage, we've got a completed refrigerant circuit. It's never been charged. It's never been tested. So the first thing we do is a safety test. We put it in a cage, which we can see over here.
And can I just ask, these are like the bicycle pumps, aren't they? These
Yes.
are the electrical compressors
Exactly that.
that'll raise
Exactly
the pressure.
that. Okay. So we completed refrigerant circuit. We put it in the cage because we're going to pressurize it for the first time. And at that point, there is the possibility that it could fail, that a part could come off under pressure at speed. And so that pressure test is in a cage. What we actually do is charge up both sides of the circuit, so the water side to 6 bar, the refrigerant side to 20 bar. Okay, we monitor it for 20 minutes. If it doesn't fail dramatically and it doesn't lose a significant amount of pressure, then it's safe for us to think about putting refrigerant in.
Okay. And you're aiming for at least 99% and above to work perfectly the first time.
First time pass rate. Okay.
So that's a really skilled assembly.
Once we've done that, we prepare the heat pump. So there are two things that we do at this stage. It takes 2 hours, but we evacuate the refrigerant side of the circuit, okay? We need those pipes to be empty of air because the vacuum will help to pull the refrigerant in, but also completely dry. So take out any water vapor that might be in there or any water vapor that's in things like lubricants that might be in the copper and that kind of thing.
Yeah.
Once it's completely dry and completely evacuated, we can put the refrigerant in, which we do by weight. Okay, so we attach them to a bottle of refrigerant, we're weighing the bottle, and we put a specified weight of refrigerant into the pump. For example, on a 6 kilowatt shoebox, we put 1.6 kilograms of refrigerant into the pump. Okay. Once we've done that, we do a final test to make sure that we're not leaking any refrigerant, and I'll walk around to it. This last test, where we colloquially call the sniff test, okay, so this sensor is designed to detect refrigerant at a very high sensitivity. So it can detect refrigerant down to 3 grams per year of leakage, which is obviously very small. When you think about we had 1.6 kilograms of refrigerant in the heat pump. The operator will go to all the joins in the refrigerant circuit and check each one to make sure that there's no refrigerant gas leaking out. Now, at this stage, that level of leakage, if it was present, wouldn't stop the heat pump working. But over a 20-year life, obviously, it would slowly degrade. Okay.
So at that rate of loss, and this is sniffing out just a few molecules of...
Exactly that.
It's highly sensitive.
Highly sensitive. The other thing is, of course, it is a greenhouse gas, so we don't want it in the atmosphere. We want it contained in the heat pump. Okay, these are high global warming potential gases, and so we don't want them leaking out into the environment.
Absolutely,
okay,
yeah.
They're carefully controlled. So once we've done this, we've got a completed refrigerant circuit. It's been charged, has no control systems and no electrics. Okay, so the next stage, which Andy's doing at the minute, is we insulate all the pipes. Right? The reason we insulate all the pipes is because those pipes get cold. Okay, they get cold, they get condensation. We don't want condensation inside the heat pump. It could cause us problems electrically. It could cause us problems in terms of corrosion over its life. So for that reason, we go and we insulate all the pipes. It also contains the heat. So it's an electrical system. Electrical systems generate heat energy. We don't want to waste that. So we try and keep it in the heat pump so that it goes into the heating system, as well as the heat that we're pumping out of the ground. Okay. Finally, if I just wander behind Andy for a minute, we're fitting the control system. So on a shoebox heat pump, the control system is on the door that is fitted to the front of the heat pump. Okay, that's the PCB, which is designed by Kensa engineers. Okay, and manufactured for us in St Austell. Okay, this entire system needs to be connected to the heat pump, wired in. Once we've done that, this heat pump is ready for test. Okay.
So there's actually a good high proportion of Cornish engineering going into each of these heat pumps.
Absolutely.
The assembly, the casing, the electronics.
And all of the Kensa designed components, the metal work is made in the UK. Obviously, we import the major components, the compressors and the heat exchangers, because those industries are European and they supply a lot of other markets. But the parts that we've designed ourselves, we try and source in the UK and where we can in Cornwall.
Brilliant. So it's a very proud Cornish industry.
It is a very proud Cornish industry.
Kensa actually is a Cornish word, isn't it?
Yeah, okay, it's Cornish for first. So, once we fitted the electrical system, it goes off into the other building and it gets tested as a heat pump. So we actually have a system there that simulates the ground array and the heating system by providing hot and cold water. We run it as a heat pump, we program its operating system, and we get it set up so that it can be used. And by that point, it's ready. We know it's working. We can go take it to final assembly and fit the housings and get it ready for shipping. So that's over here. So at final assembly, you can see all the housings to go on. We actually add some insulation, so I'll just grab one. So we add some insulation to the heat pump. This is primarily, it's what I mentioned earlier, keep some of the heat in, but also an extra layer of noise protection so that the heat pumps are nice and quiet. Typically, these things sound pretty much like a fridge. So the same sort of noise levels as your domestic fridge. So we fit the insulation to the housings, fit the housings, apply the labels, that kind of thing. And then we pack it on the shoe boxes. The small shoe boxes are designed so that we can put a number of them on a pallet. Obviously, they're targeted at these larger projects for social housing, the blocks of flats. So we might be delivering 100, 200 to a site. So they go 8 per pallet and off they go. The larger shoe boxes, 1 per pallet. So bearing in mind that this factory will make anywhere between 24 and 30 heat pumps a day. When we've got 1 per pallet, that's a truckload. We literally fill a truck, send it off to the project somewhere in the UK. For the smaller ones, so much easier, 3 pallets, 24 heat pumps. So one of the things we need to do and we intend to do is to improve the packaging, both to make it more environmentally friendly where we can, more recyclable, but also to actually minimise our shipping, again, carbon impact. The more we can get on a truck, the better.
And we're expecting each of these heat pumps to last around 20 years.
Around 20 years, could be longer.
And at the end of the life, it's already written into the engineering that when they're decommissioned, they're taken apart carefully, the refrigerant's extracted,
yes,
recycled, along with the whole machine being recyclable.
Exactly that. So almost all of the parts in the heat pump can be recycled in one way or another. So all of that goes back to recyclers. As you say, the refrigerant has to be managed very carefully. It gets extracted and returned to the guys who make refrigerant, who reprocess it.
So what a fantastic tour, and I hope you all enjoyed that and saw how they're actually putting these things together right here in Cornwall. So that's really, really exciting. We've got a few minutes. I'm going to speak to Darren very quickly about how we put these things into the ground. So you've actually seen how the pipe work and everything's put together. How do we actually get the heat out of the ground? And that's the important part. Darren, maybe you can tell us a little bit about the kind of where we get the heat from. How does it work in terms of coming out of the ground? What do we need to consider?
Okay, so the way we harness the energy stored in the ground is via what we call a heat exchanger, or a ground array, okay, rather. As Paul's explained through the process, when the pump comes on inside the heat pump, they talked about the refrigerant circuit, and what the refrigerant actually does is absorbs 5 degrees from the ground temperature that we pump into it. So, for example, if the ground array comes in at 10 degrees, because that's the heat energy temperature of the heat energy stored in the ground outside your property, we can use that, pump that through that first heat exchanger, the evaporator, take that refrigerant absorbs the 5 degrees from it, and then it goes back out at 5 degrees. And by creating that lower temperature, we enable the ground temperature that's stored in the ground to actually transfer into the pipework or into what we call the ground arrays, which is essentially your battery for your heating system.
And you need to consider as well, so we've got here boreholes, slinky pipes, pond mats. What's the difference?
Yeah, okay, so boreholes are primarily used where there's very little surface area around a property. So if you've got a high-rise tower block or something like that, they don't often come with loads of garden and there's very little space outside. So you might find that a borehole is more suitable.
And that's where you go directly down into the ground. And how far do you go?
Vertically drilled can go anything up to 230 metres, something like that.
Okay.
I've seen some slightly deeper.
Okay.
But essentially, it's the same pipe. It's just MDPE pipe.
Okay.
Goes down the borehole and back up.
Yep.
Slinkies are a Kensa product. Essentially, it's just straight pipe that's pre-made in the factory here.
Okay.
We make them into loops.
Yep.
But when you roll out the pipe back in the ground, it's basically we need a lot less digging with a slinky, and it's the same principle. It's just lower temperature water than the ground temperature, and it absorbs that ground energy.
Fantastic. So I think we need to move on to the next part. Thank you so much, Darren. And now you have a challenge to do, an engineering challenge. And this is really important so that you can practice solving unfamiliar problems. This is what engineers do all the time. And you're also going to be doing careful calculations. Very important as an engineer or a scientist as well. So for this challenge, as a class, you're going to all work together to solve this. Now, we're going to pose you a problem. It's on your worksheets, and your teacher will go through it with you. But what we're going to ask you to do is to calculate how much you increase the temperature of 20 litres of water in a house by heating it from a typical, much larger ground array. So just as Darren was talking about here, you take a really big area of ground, you take a lot of heat, and remember what Adam was saying about the fact that heat and temperature are very, very different. We're taking a lot of heat from a really large area, and we're condensing that into a smaller area. So all we're asking you to do is to think about the amount of heat you're going to exchange from a large area to a small area. In this case, from 200 metres of pipe, 32 millimetres in diameter, and you're assuming in this case a water temperature change of 3 degrees Celsius. Seems a bit strange and probably seems a bit unfamiliar for you, but this is part of an engineering challenge. You need to solve unfamiliar problems as an engineer, work in a team, work with your colleagues, have a go. You've got 5 minutes. Thank you very much.
So, welcome back, everyone. What I'm going to do is to run through the ways of looking at the problem that Natalie set you. And in fact, you can look at this on 3 different levels. We can look at a very simple way of solving the problem partly. We can do a more complex method. And then there's quite a complex method that's the full real answer. The answer I expect you to have got to the problem that was set is that the temperature of the 20 litres of water goes up by around 24 degrees centigrade. And the reason behind that is when you calculate the volume of liquid, it's a water with anti-freeze and anti-corrosion materials in it going around the ground loop, we can work out the volume of that fluid in the ground loop. We do that by working out the cross-sectional area of the pipe by pi times the radius squared by the overall length of the pipe. And we were told that the diameter was 3.2 centimetres, the radius is 1.6, and this gives us a cross-sectional area of just over 8 centimetres squared. And if we multiply that by the length of the pipe, 200 metres, we find that the volume of the ground loop is just over 160 litres. I think it comes to about 161 litres. And if we were to think of this simply, we'd got 161 litres of fluid picking up heat energy from the ground, and we're trying to heat 20 litres of fluid, perhaps going into our hot water tank or into our house heating. 160 litres is 8 times the 20 litres. So if the ground loop went down by 3 centigrade, we could, on a simple basis, say that the 20 litres would go up by 8 times that amount if we simply shifted the heat from the ground loop to the 20 litres. We could go a little more complicated by knowing the specific heat capacity of water, which is 4.2 joules per gram of water per centigrade or per Kelvin, or 4,200 per kilogram of water. And we could do it that way. The absolute complex way takes into account something called coefficient of performance, which you may have read about in the slides that accompany this lesson. And in fact, if the coefficient of performance of our heat pump was round about 4, which is a realistic figure for a ground source heat pump, or maybe even a little above this, we'd say that 3 units of heat were taken out of the ground and 1 unit of heat was coming from the electricity that went into the heat pump. And we'd find that that 20 litres of water, in fact, didn't just go up by the 24 centigrade. There would be a third more from the coefficient of performance going on to that. So the real answer would be it would be going up by about 32 centigrade. These are very efficient machines. And I hope this little calculation has shown you how we can take low-grade heat at a low temperature across a large area of ground and concentrate it into the smaller volume in the house, raising its temperature phenomenally. Thank you, everyone.
Brilliant. So, thank you. Thank you. So we haven't had any questions in from you yet, and I know some people are having some problems with the chat, but basically, this is a time to be able to ask questions to all these wonderful engineers and find out more about their backgrounds and stuff. So we'll just ask them some questions for you. So yeah, we will start with you, Ben. Would you tell us a bit about just how did you get where you are? Why are you doing this?
Yes, so I was working in the aerospace industry prior to this, and it might be a bit of a misconception, but actually things like aerospace, although they are large polluters, stuff like that is only 9% of the UK's anthropogenic CO2 emissions. Whereas domestic heating and commercial heating is about a third of the UK's CO2 emissions. So I was really interested to work in an area where a bit more of an impact could be had in improving devices that have been described like heat pumps, and you can help reduce the UK's emissions.
And so how did you get into aerospace engineering? What was your sort of career path, your education path?
Oh yeah, so I did started with quite a sort of standard route of going to college, doing A-levels, going on to do an undergrad degree at uni with work placement. And then I actually ended up doing a PhD sort of in an aerodynamics topic, which just kind of came about from enjoying those aspects of my undergraduate course, which was aeronautical engineering. But with the way engineering's taught at sort of higher education level, you do get quite a lot of the fundamentals, so it does make it quite nice to be able to transition between different subjects, particularly within like mechanical engineering disciplines.
And maybe can I ask the same question to each of you, actually. Yeah, thank you.
Okay, yeah, so Ken's actually my first introduction to engineering. So I was in a different line of work, mainly sort of software sales and support, and I fancied something new. So I looked for a job, and there was a job here at Kensa on the production line, so I started here. I was testing heat pumps right at the end of the production line where you hook them up to the rig, and doing that you get to learn a lot about some faults and how they work and what you need to plug in if this is doing the wrong thing. So through that, I got quite a good understanding of the way they work. And then a position came up in R&D to do the accredited testing. So when we develop new products, we have to test them, which I was doing. And as the team grew, I was offered the opportunity to develop my own team in doing that from now on. So I sort of run a team that does all that accredited testing and builds prototypes of the new exciting products.
Wonderful. And how about you, Darren?
I came from a completely different background. So we've got these wonderful engineers, as you've just met here, and Paul as well, engineers. My background was the heating side. So I was an installer, and I'd install plant rooms like this. So what we learned at Kensa was that heat pumps, they're fantastic, and we've got fantastic engineers that design them, and we sell those boxes, but they need to be integrated into a system. What we found was we needed a link to installers and how to install these bits of kit, and that's where I came in. So a bit of a training background. I'm more of an installer, so I'm not really an engineer on the same level as these guys. I don't understand too much what goes on in the technical detail of it, but I do understand the system. So I can integrate the product into somebody's home, and that's where I come in.
Fantastic. Brilliant. Paul, how did you get here?
It was a long path. So years and years and years ago, I studied electronic engineering with computer science at university. After having done A-levels in physics, computer science and maths, I was all lined up to be one of these geniuses and spend my life in engineering design, because that's what I thought I wanted to do. But actually got into doing research for what was the Ministry of Defence Research Agency, sonar systems, really getting down and dirty with the maths and the science and that kind of thing. And then eventually I kind of went, I want to go and see something more commercial. So I spent about 10 years working in consultancy, working with big companies, Vodafone, the people who make Blackberries, Ford, and that's where I learned about manufacturing, how to make stuff, and I kind of really, really enjoyed that. So from there, I actually went to a company that, I was running a company that made electronics, and that was my move to Cornwall, how I got to live in Cornwall, which is lovely, and then is also how I knew Kensa. And 2.5 years ago, the opportunity to join Kensa, because Kensa's growing, and they need somebody to take over running the factory, the new factory I've just walked you around. And for me, it was the chance to really get involved in the renewable side of the business, making a difference to the planet. That's why I was attracted to it. And yeah, since then, it's been all about trying to figure out how we make more heat pumps, how we get more of them into UK homes, in the future, more into European homes. So really, join this mission driven by two guys who started their engineering career in a garage, convinced that the best way to heat a house was to pump heat under the ground. They started Kensa. 20 years later, this is it. 20 years' time, this is going to be massive, because this is what we've got to do to improve, build a UK heating infrastructure that really doesn't destroy the skies.
Yeah. Fantastic. So we're in the amazing plant room right now, which is just a beautiful thing to behold. And these are your own big heat pumps here, right? These are,
Absolutely.
yeah.
So this plant was relatively new because that part of the factory that we walked around is 3 years old. Okay, so both parts of the factory are heated with underfloor heating. The heat for that comes from the mine, because this used to be a tin mine, and there's a mine shaft just over there with a bunch of pipes dropped in, and these heat pumps are taking that heat, squishing it up into underfloor heating in the factory and an air exchange system in the offices above. One of these, I think it's that one, Darren, tell me if I'm wrong later, is actually dedicated to doing cooling. So we also have the ability to pump the heat out of the offices and back into the mine shaft so that we can use them for both heating and cooling.
Fantastic. We have had a question. Wow. So this is from Paul at Truro and Penwith.
Hello, Paul.
So do Kensa do air heat pumps, and do these differ?
We don't do air source heat pumps, and that's because we are so stubborn, in the sense that we're absolutely convinced that ground source is the best way to do it. There's a combination of factors there. Talk to you about what is fundamentally different. Fundamentally different is you take the heat from the air. There's nothing wrong with that. It is certainly better than burning gas, right? There is a slight improvement when you take the heat from the ground, and the reason is this, right? In the winter, when you're trying to pump heat out of the air is already cold, your heat pump has to work harder. So we talked about coefficient of performance earlier. Coefficient of performance on air source drops in the winter. Still works, still fundamentally, you've got a COP, you're getting some increase in efficiency, and you're taking the heat from somewhere and putting it in the house. For ground source, typically for the UK, the underground temperatures are constant all year, it's about 12 degrees. So in winter, ground source is actually more effective. There's going to be something, isn't there? Okay. We decided as a business that we would focus on ground source and be the best people doing that in the UK, and currently we're the market leaders for that. There are others, I think from our perspective, the more people selling heat pumps, the better. But we focus on ground source.
Dave from Callyworth College, thanks so much for sending this through, Dave. Have you thought, this might be one for one of the engineers, have you thought about using aerogel as an insulator, I suppose, around the air source, around the ground source heat pump?
So I have actually, I've heard of the brand name aerogel, but I'm not entirely in memory of exactly what it is. But in insulation around the heat pumps, any way that you can sort of insulate, I believe Paul mentioned it as part of the tool, any material that can be used that has a really low thermal conductivity to trap any heat inside the heat pump is a really good thing. That would be inside the heat pump, but it could be something that we would look into in future, because, yeah, you do want to conserve any heat that you possibly can once you've put the energy into it to raise its temperature.
Fantastic. And we've got a couple more questions, so if you've got any more, please do send them through. We're going to anticipate one, because there's always one that comes up in every one of our live stream events. I'm sure you all want to know how much a typical engineer earns in terms of salary. This is one that comes up every time, so I bet you're all wanting to know. Maybe we can, who wants to volunteer?
So I guess I could say one thing, and maybe not that much, and the reason I wouldn't say is because it is really broad. So engineering is, you've got to think there's many different areas of engineering, electronic, more mechanical, software. You've also got the opportunities that engineering companies are quite large institutions. You go through various levels of management. So you can, I won't give a number just because it really is so broad. So you can earn typically from a very sort of competitive graduate scheme wage up to the levels of CEO and managing directors from this career path. So it is incredibly broad.
So, if we want to explain why you do career in engineering, yeah, okay. You know, when I, as I mentioned, when I started, I was fixated on being engineering and in terms of design, okay. But engineering in itself is so multifaceted, and just think about the fact that the guys who started Google were engineers. You know, the guys who Steve Jobs, who started Apple with Steve Wozniak, was an engineer. You know, so in fact there is no limit, and for me, engineering is about people who enjoy the imagination and the creativity involved in solving problems. If you think about stuff all the time and you try and work out how to change it or make it better or why it does what it does, you know, that enthusiasm in engineering is what ends up in, you know, incredible products like your phone, like your car, like your heat pump, you know, and it's the engineers who will solve the problems that save the planet.
Awesome. I've got a question. So obviously there's this big government push to install heat pumps and to find alternatives for heating. Can just anyone have a heat pump? How easy is it to get a heat pump?
Really easy. I think this is the reality of what a heat pump is. We're producing one every 15 minutes at the moment, and I was talking to somebody recently who works in a car plant, and in a car plant they make one every 2 minutes. Okay, we will be there in 2 or 3 years' time, but the level of complexity in a heat pump versus a car is tiny. They're a really simple product. Okay, the science has been around forever. Fridges have existed forever. A heat pump is a backwards fridge. Okay, so the technology is available now. We don't have to do any magic. We don't have to do millions and millions of man-hours of science to figure out how to use these in our houses. The science for how we put a ground array in the floor is understood. So frankly, we can put them in almost anywhere. There are very few geologies that you can't put a ground source array in. Okay, and installing a heat pump is no harder than installing a boiler. So actually, yes, everyone can get these. The driving factors at the moment are getting it accessible, getting the support from the government to push this forward, which they've started to do, and then getting everyone to understand that it's just a source of heat. It's as good as a boiler. Put it in your house.
Brilliant, thank you. Fantastic. So we're going to round off there. Thank you all so much for taking part. From our wonderful engineers who really enjoyed being here, and especially I'm really enjoying as a former engineer being inside this plant room. This is really very, very nice indeed. So we're going to say goodbye now. Thank you so much for joining us. And Adam's going to give you a very quick summary, bringing all that together. What are the key things that you need to take away from this session? Over to you, Adam.
So what we've learned today is that the heat pump is an incredible machine. Around 40% of our global warming problem is related to buildings, especially to heating buildings and cooling buildings. And a heat pump is a device, an ingenious device that does that so much better than the fossil fuel boilers, the gas boilers and the oil boilers that we're all used to. A few years from now, the majority of buildings that you'll see being built will have heat pumps in, just like the Kensa machines that we're looking at today. The heat pump is a device that takes low temperature, low grade heat from the environment, concentrates it using the thermodynamic circuit we've looked at. And if we can drive that thermodynamic circuit using renewable energy electricity to drive the compressor, it is a carbon neutral machine to run. I run one of these in my house and have done a Kensa heat pump for the past 8 years. It works perfectly. I run it off renewable energy at low peak electricity times, and it has a minimal carbon footprint on the world. Yet it keeps the home beautifully warm. And that's the message to take away from today. And of course, we're all at school and college here in Cornwall. This is a proud Cornish product where Cornwall is one of the leading places in Britain, Europe and the world. So thank you for joining us.
Fantastic. Thank you so much, Adam. We've had one more question coming in, so we're going to answer it really, really quickly. This is from Max at Truro and Penwith College. I'm going to ask this to Paul. If you can tell us, can heat pumps only be added to new developments, and do Kensa employees have heat pumps in their homes?
No and yes. So only new developments? No, not at all. There's a huge retrofit market. So one of the things that is currently very fashionable is taking out your oil-fired boiler, because oil is currently extraordinarily expensive, and replacing it with a ground source heat pump, because that is a really good way to save on your energy bills. The other end of that scale, if anybody visits Trelisic House in Cornwall, we've recently commissioned a cascade of 6 of these heat pumps in Trelisic House, retrofitted without doing any serious changes to the house, because we wouldn't be allowed to do that kind of thing. It's heated from boreholes in the grounds just in front of Trelisic House. So yeah, we can retrofit or we can put new build. Do Kensa employees? Yes, there are a whole collection of Kensa employees who have heat pumps in their homes.
Fantastic. Thank you all so much. Thank you very much for joining us, everyone. And please fill in your feedback forms next. That's really, really valuable for us to tell us if you've enjoyed this event, how we can improve. So please do fill those in, teachers and students. But from all of us here at Kensa Heat Pumps here in Truro, near Truro, Cornwall, thank you very much for joining us. Bye.